Okay, welcome back. We're in 5.2, which is on scientific notation. And to begin this lesson, we're going to look at multiplying numbers to start. So, for example, specific numbers, if I multiply by powers of 10. So, if I have, say, some number like 2.3, and if I multiply that by 10, multiplying something by 10 just moves your decimal place over 1, so this 2.3 becomes 23. Right? I'm going to give myself a little room here. Let me just multiply it by 10. Shove that off to the side, just you'll see why later. Right? So if I take that same 2.3 and let's say I multiply it by 100, right? That's like 2 tens. It just moves the decimal over once and then once more, so that's 230. Right? And again, I can keep doing this. 2.3 times, if I have a whole bunch of, like, say, 1 million. Right? That's just moving the decimal over to the right, however many zeros are in this number. Right? There's 6 of them, so that's move it over once to get the 3, and then 5 more gives you 5 zeros. And I have 2,300,000, right? And so it's this phenomenon that we can see happening no matter how big, I multiply by a billion, a trillion, a quadrillion, whatever, it's just moving that decimal over, right? And so in this little space here, we're going to rewrite this because these numbers get pretty big. They can get pretty big. But I could have also written this as 2.3 simply. Here I would just write it as 10 to the 1 because there's just one power of 10 here. There's not anything terribly special about this one. This one here, though, I can rewrite as 2.3 times 10 squared, right? Because 10 squared is 100, and so I have 2.3 times 10, and then times 10 again. And here I just have times 10, times 10, times 10. Well, there's just 6 tens hidden in this 1 million. So I'll write this as, if I have room, 2.3 times 10 to the 6, right? There's 6 zeros there. That's 10 times 10 times 10 times 10 times 10 times 10, right? And that's the nice magical part of this numbering system, this scientific notation, is if I end up having a really huge number, something like that. Hopefully it didn't go off the screen. Scooch it. Yeah, that's all right. Okay. If you come across this, it may even be difficult to see this on the board from this video camera, but if you read this in a book, if you have a whole bunch of zeros, it might be hard to see this number. But I can rewrite this in this fashion, right? I can write this as simply, well, it was like taking 2.3 times, well, how many zeros did I have to move? Well, I had 3, 4, 5, 6, 7, 8, 9, plus that last digit place to get that 3, so there's 10, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But again, this doesn't look any better. This actually looks worse. It's this middle number that makes everything kind of look nice. And so I would write this as simply 2.3 times 10 to the 10. And this number is in scientific notation. It's easier to read. It's just a 2.3 that gives you kind of the magnitude of the number, or the value of your first digit places. And then this times 10 to the 10 gives you the magnitude, right? So that's the power of the scientific notation. Let's take a look at an example. That in the book they have the mass of the sun written out. That's a perfect example of seeing a number and saying, oh, I don't even understand how big that is. Alright, so it's a rough, like the first, they have 4 digits that are accurate, and then after that it really doesn't matter because we're talking about a tiny fraction of the whole. But this number is huge. It's 1, I think it's 989. That. And that's a ridiculously long number, right? If you came across this number, you're just like, oh yeah, it's some humongous number, right? This is kilograms, and that's about how big the mass of the sun is, right? So if you see this, it's like, well, it's huge, and you'd have to sit here and just even understand the magnitude of the number and count the zeros, 1, 2, 3, 4, 5, 6, and you lose your place probably. If you came across this in a book in 12-point font, it's ridiculous to try to read one of these numbers, right? So instead we would have this written in scientific notation, and in scientific notation there's 3 steps really. The first step is to place a decimal after the first non-zero, and by first we mean the leftmost, non-zero digit. Okay. And then after that, 2, you're going to get rid of all of the non-essential zeros. The non-essential zeros in a large number are all these zeros that trail after this 9 in this number, right? There are some zeros that are essential. For example, if I had something like 1,000 or something, you know, something like this, some big number, whatever this number is, it doesn't matter, 1,050,000,000. This 0 here is essential, because there's another non-zero digit after it. But once you hit this first 0 where everything after it is zeros, these guys are non-essential zeros, and we're going to eliminate them. That way we don't have to write this ridiculously huge number. But again, this 0 here is essential. We want to get rid of the ones that are non-essential, and that's all of these zeros that are just followed by zeros. Right? And then 3, the very third and last step would be to write multiply by 10 to the appropriate power. And this works for both. We're going to do 2 things. We're going to take really big numbers like this and write them as scientific notation. We're also going to take really small numbers, but these 3 steps are the same. I'm going to erase them because I need the space to work on this big number, but these are the steps that we're going to go through. So the first step was to place a decimal after the leftmost non-zero digit. So that is to say I have 1 point, that decimal goes right there, 989. And then step 2 is to not write all of those non-essential zeros, right? And then step 3 is to simply multiply by the appropriate power of 10. 10 to what power will turn 1.989 into this ridiculously long number? And so you just count the number of decimal places that would be moved. So there's 3, 6, 9, 12, 15, 18, 21, 24, 27, 28, 29, 30. Okay. And that's my number in scientific notation, because if I took this number and actually multiplied it by 10 to the 30, I would move that decimal place 30 places to the right and obtain this number. Right? And so I have it in scientific notation. This is much easier to look at. It tells me the magnitude right off the bat. It's times 10 to the 30, and it gives me that first, 4 digits in this case, right? All right. Let's take a look at a few numbers and write them in scientific notation. Just random big numbers here. There's a big number, right? To write it in scientific notation, that decimal goes after that first non-zero digit, so that's 2.73. Get rid of all of my non-essential zeros, and then write multiplied by 10 to the however many digits were moved, right? So there's 3, 6, 9, 12, 13, 14, 15. There's another big number. Same thing, I'm going to put that decimal after the 3 here, so 3 point. And then I have 1, 5, and this 0 is essential. Don't get rid of it because there's a number after it that's not 0. So 3.1502, and then times 10 to the, there's 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 places to move that decimal from after that 0 all the way up to this 3. So I think I said 17, yes. All right. And there's our number in scientific notation. Now, that illustrates taking really big numbers and writing them as in scientific notation. It has its limitations though, right? If I have a number that's say 215, and I write this in scientific notation, it now looks worse, right? This is scientific notation, but it's not particularly helpful because it's easy to understand what 215 is. This takes a couple of seconds of thought process to say, oh, 10 to the 2, that's 100, multiply that by 2.15, well, that's just 215, right? Or if I had something like 37, and if I write that in scientific notation, that's 3.7 times 10 to the 1, right? Once again, not terribly helpful, right? I know what 37 is, 3.7 times 10 to the 1, I gotta look at that, and it's a lot bigger to write that than it is to write 37. There are some books out there, super nerdy physics or math books, where they write their page numbers in scientific notation, which means when you start and open the book on page 1, it's not written as 1, it's written as 1 times 10 to the, well, I'm not actually multiplying it by a 10, so there's no 10s here, that would be 10 to the 0, right? You open it up and you start on page 1 times 10 to the 0. Again, that's just page 1, right? There's little value here. In these numbers, right, 1 digit, 2 digits, 3, maybe even 4 or 5 or 6, there's not a whole lot of value there. I can look at the number million and say, hey, that's a million, but if I look at 1 times 10 to the 6, you know, there's not a whole lot given to me, there's not a lot of time saving to look at that number, right? So, but those are our big numbers, right? And that's why we reserve it typically for really big numbers, once you start hitting trillions and so on. But we can also look at very small numbers, and it can be very helpful. And I don't mean these kind of small numbers, I mean super small numbers. Such as, I want to say there's the mass of an electron in this book. I'm going to look at it here. Let's see, there we are, yep it is. 0, if I can remember how many zeros there are. The mass of the sun, a really, really big thing, versus the mass of an electron. And again, it's an approximate. Let me find out how many there are here. Oh, I don't see that it's worked out in the book, so from memory, I want to say it is that number that I had to write super small. I made it on the screen though. If you read this in a book, it's even worse because on the right-hand side in English, we don't throw commas, right? So it's just a whole bunch of zeros crammed into each other, and it's hard to even look at this and say, hey, I can understand the magnitude of this, right? So with a very small number like this, scientific notation again comes into play. Before we mess with this number though, let's take a look at, let's start with our 2.3, and instead of multiplying it by 10, I'm going to divide it by 10, right? 2.3 divided by 10 simply moves my decimal the other way. So this is 0.23. That decimal comes in front of the 2, right? 2.3 divided by 100 just moves it over twice. And so that's 0.023, right? And you can see how I can turn 2.3. If I just keep moving this decimal over and over, it might start looking like a number like this. Right? Obviously the numbers are different because it's 2.3 and 911, but let's go 2.3 divided by 1,000 is just moving it over one more time, right? And so if I have some number, say 0.00000023, that's probably below the screen. Nope, it's not good. My lines are not great then. Then I can turn that into, say, 2.3 divided by however many times I move that decimal place to the left. So 1, 2, 3, 4, 5, 6, 7, 8. Right? Divided by that many. But again, I can rewrite these. Instead of dividing by 10, I can write this as, instead of divided by 10, I can write this as multiplied by 10 to the negative 1, because 10 to the negative 1 is like having a 10 in the denominator, and therefore times 10 to the negative 1 is the same as dividing by 10. Likewise, instead of dividing this by 100, I can write this as multiplying by 1 over 100, or 10 to the negative 2. And I can write this one as multiplied by 10 to the negative 3, and I can still then use that method that we use for the big numbers, but this negative means that we're shifting that decimal to the other direction, right? So instead of 2.3 divided by this, I have 2.3 multiplied by 10 to the negative 8 will give me that number, right? So I'm going to go through the same steps. Step 1 is to put the decimal to the right of the first non-zero digit. So I'm going to erase this and get to this electron mass. Step 1 is to take that 9.11 and I'm going to eliminate all of my non-essential zeros, which for this is all of the zeros to the left. That 0 right there is the first 0 to the left that has nothing but zeros to the left of it, so they're all non-essential, right? And so 9.11, and then I simply write times 10 to the, it's going to be negative, right? And it's however many decimal places I moved. So this number's horrific. I have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31 places. And this is again much nicer to come across in a book than this, right? Let's take a look at a few more examples of this. If I have, for example, let's just say some 0.0000000000045, right? I'm going to take that decimal and put it after the 4, so this becomes 4.5. Eliminate all of these zeros, right? Times 10 to the How many places do I have to move it? Well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. So I would have to move it 10 to the back, to the, the negative, to the left direction from here to get back to my original number. And so this number is 4.5 times 10 to the negative 10. This number, once again, that decimal comes to the right of the first non-zero number, so that's 2.0. That 0 is essential, so I need to keep it. 2.03 times 10 to the negative. Well, from here I would have to have gone 1, 2, 3, 4, 5, 6, 7 places to get back to where I started, so that's times 10 to the negative 7. And I have this number in scientific notation. Okay. So that's our very small numbers, and again, it's limited in its usefulness. For example, if I had the number 0.25, and I were to write this in, you might recognize this as a quarter if you've done your fractions to decimals conversions. Right? And it's pretty easy to understand, 0.25, but if I write this in scientific notation, it's 2.5 times 10 to the negative 1, and again, there's not a lot of value added here. There is a lot of value added on these guys because it makes it shorter, gives you the magnitudes right off the bat, but this number is probably harder to understand than this one, because this one takes just a couple of seconds of, oh wait, yeah, move it over, and it is this number. But this one's easy to understand. Right? All right. Now, the biggest amount of added value here is, excuse me, I'm sorry. When I have very large numbers multiplied by very large numbers. Let's go 3 more, why not? Right? If I try to take these two numbers, and I'm say doing this on paper, I don't have a calculator handy, and this is actually how calculators do it anyway, but if I have these numbers and I have to just multiply them by hand, and I write them out, this multiplied by in our typical multiplication algorithm, we start here at this 0, and I'm going to take this 0 and multiply it by that 0, and then that 0, and then that 0. So 0 times 0 is 0, 0 times 0 is 0, 0 times 0 is 0, times another 0, and another, and another, and another, and another. Great. That takes care of this 0. And now I'm going to move on to this 0. To multiply this 0 that's in the 10 spot, I'm going to add a 0 here. I'll put an X through it just to note that that 0 came from my place movement. And this 0 times each of those digits, which are all zeros. And then this next one gives me 2 place movements, and then a whole bunch of zeros, right? See what I'm getting at here? Is I'm going to have this humongous cascade of zeros before I even get to this number, which will give me even more zeros before I finally get this 3 times this 3. So I'm going to have 1,000 zeros hanging out here, and it's a waste of time, right? It's a waste of time and a waste of energy and a waste of my marker boarding, right? So instead of doing it this way, terrible, right? I'm going to rewrite these numbers in scientific notation first. So I'm going to write this as then 2.3 times 10 to the, what is that, 3, 6, 7? and then that gets multiplied by 3. And if there's not anything after the 3, there's only the one digit, I don't need 3 point anything, because it's just 3. It's 3.0, but that's the same as 3. And then multiplied by 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So really I have this number, 2.3 times 10 to the 7 multiplied by 3 times 10 to the 12. But this is multiplication, and multiplication is commutative. That means I can take 2.3 and multiply it by 10 to the 7, and then multiply it by 3, and then multiply it by 10 to the 12, or I can take 2.3 and multiply it by 3, and then multiply it by 10 to the 7, and then multiply it by 10 to the 12. I can reorder this, right? I can rewrite this, that is to say, as 2.3 multiplied by 3, it's commutative, right? I can say switch places. It's also associative, which means I can multiply these two first and then multiply these two, right? Well, 2.3 times 3 is easy, right? That's 6.9. But 10 to the 7th and 10 to the 12th are two 10s raised to powers, and so I can just add those powers together. And so this is still multiplied by 10 to the 7 plus 12, 19, and I'm done. There it is. It's a 6.9. All of those zeros would add up and crush together to be simply 19 decimal places long, so 18 zeros after that 9, right? And that's my number. It's in scientific notation already, and I'm done. I don't have to worry about anything else here. Right? Let's do another one. Let's look at a really big multiplication. Let's say I want, let's see, let's start here. I want that multiplied by that, perhaps, right? So again, I'm going to rewrite this as 1.2 times 10 to the 3, 6, 9, 10, 11, 12, 13, 14, 15, and then multiplied by 2.765 times 10 to the 3, 6, 9, 12, 13, 14, 15 as well. Right? And so all I have to do is figure out what 1.2 times 2.765 is. Okay. So 2 times 5 is 10. Two times 6 is 12, plus 1 is 13. 2 times 7 is 14, plus 1 is 15. 2 times 2 is 4, plus 1 is 5. Right? Get that 0 placeholder, get rid of my carry marks from my last run through. 1 times 5 is 5, 1 times 6 is 6, 1 times 7 is 7, 1 times 2 is 2. Add these up. Alright. You should probably practice doing this by hand instead of jumping straight to the calculator. But I have 33180, right? And if you remember multiplying decimals, there's 4 total digits after the decimal in the problem, so there should be 4 total digits after the decimal in your solution. So you get 3.3180, which is the same thing as 3.318. I can get rid of the 0 for the same reason I can get rid of the non-essential zeros when I write it in standard scientific notation. Right? But that's these two numbers multiplied together. That was 1.2 times 2.2765. And so I end up with that, 3.318, times 10 to the 15 plus 15 more, that's times 10 to the 30, It's in scientific notation, so I'm done. If they ask me to write my answer in scientific notation, it's already there. Now that's not to say that this will always be the case. Let's take a look at an example where it's not. Where your answer is not in scientific notation when you're done with it. Okay. Such as in this problem. So that's 4.2 trillion times 63 million. If I write this in scientific notation, that's 4.2 times 10 to the 3, 6, 9, 10, 11, 12. Multiplied by 6.3 times 10 to the, there's 3, 4, 5, 6, 7, right? And so if I multiply my numbers, this 4.2, this 6.3, 3 times 2 is 6, 3 times 4 is 12. Scooch over, 6 times 2 is 12, 6 times 4 is 24, plus 1 more is 25. 2 digits after, oh I should add them, 6, 4, 6, 2. There's 2 digits after the decimal in the problem, so there should be 2 digits after the decimal in the solution, so I get 26.46. Times 10 to the 12 plus 7 more, that's 19. If the problem says, here's 2 really big numbers, multiply them and write your answer in scientific notation, this is not in scientific notation because that decimal is not to the right of the first non-zero number, right? So to write this in scientific notation, I have to move this decimal, I have to correct it. Right? And to think about what power of 10 comes next, right? This number up here, this says from here the decimal has to move to the right because that 19 is positive 19 spots. So positive 19s to the right 19 spots. But now to get the same number, I'd have to go 20 to the right to get to the same spot. And so this is times 10 to the 20, right? And I have to make that correction if the question says, put this in scientific notation, I have to make that correction. Right? This is not scientific notation, this one is. Right? All right. Let's take a look at really small numbers that multiply together. Let's take a look at, let's say, 0.00000000021 multiplied by 0.0000032. Again, I'm going to, just like I just did, I'm going to rewrite these in scientific notation. So this first one is 2.1 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces times 3.2 times 10 to the negative 1, 2, 3, 4, 5, 6. Right? And again, I can rewrite this as 2.1 times 3.2. That times that, and then multiply that by 10 to the negative 9 times 10 to the negative 6. I don't need these parentheses, but it's indicating that I can just multiply these two to get a number, and then combine my powers here to have 10 to some power. Right? 2.1 times 3.2, 2, 4, scooch over, 3, 2. 2.72 times 10 to the, you're adding these, but they're both negative, so that's -9 plus -6 more, that's -15. And I'm done. It's in scientific notation because the decimal's in the right spot. Voila, done. Right? Okay, let's look at one last one. Let's look at a very large number multiplied by a very small number. That number multiplied by that number. Right? This first number written in scientific notation is 3.4 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Multiplied by 8 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. So I can take 3.4 and multiply it by 8. Eight times 4 is 32. 8 times 3 is 24, 25, 26, 27. One digit total after the decimal, so I have 27.2. Times 10 to the 16 plus -17, that's -1. And if I want to change this into scientific notation, I have to go back, and so that's 2.72 times 10 to the, and again I had to increase my power of 10 by 1 because I moved it to the left, and so this becomes 10 to the 0. You can think of this as this 27.2 became smaller, so the power has to compensate by becoming bigger. But times 10 to the 0 is 1. And so at this point, there's no point in writing this in scientific notation. I can just write this as 2.72, and that's my answer. If it says to write it in scientific notation, then yeah, you do need the times 10 to the 0, but the answer itself is equal to 2.72. Good. All right, thank you, and I'll see you guys next time for 5.3.